we'll study this time response of linear dynamical systems in state space form in this lecture actually. So, we are here at lecture number 18 now, and previous lecture we have derived this linearization, in other words linear systems about operating point for nonlinear systems. We discussed that, and this particular lecture will study this how do we get a time response or the system solution actually, okay, for the linear system equations actually. But before that, let me correct a small mistake that we observed actually what I did in the previous lecture. So, this example we discussed in the previous lecture where van der Pol oscillator, and this was the nonlinear system, and if you recall there was this particular term, okay, in other words this term was taken as 0 actually, which is not true, because once you have this equation, I mean this second equation here, and you take a partial derivative with respect to x1, you are having this term which is a constant term, okay, there is not associated with x1 anymore. So, that is how this constant term will appear here, and the A matrix will turn out to be that way. So, it is not like 0 0 here what we discussed in the previous lecture actually. Sorry for the mistake, but this is the correction what we need to do. Anyway, let us continue with the time response of linear dynamical systems in state space form actually. So, what is I mean very quickly, linear systems are very nice because of two major things. One is they satisfy this principle of superposition, otherwise by definition they are not necessarily linear systems. So, we are not worried about that. Okay. So, then the uniqueness theorem is also very great because it tells us that there is only one solution for the linear systems. That is a great uniqueness theorem actually. Means these systems will never admit multiple solutions. So, these are some of these great things why this linear systems theory is very handy to deal with actually. One is the system stability nature is independent of initial condition, that is another one. Okay. And then this one it talks about the system can have only one solution actually. Okay. So, let us but we will not prove this. I mean what we want to do here is want to exploit this result actually. Okay. So, let us start with a small scalar case again, and then we see how to build up there actually. So, and the scalar homogeneous linear differential equation, I mean in my view nothing can be simpler than this. We have this x dot equal to x with initial condition x of t0 is x0. Okay. So, what is the solution? It is a plus 2 calculus sort of thing, plus 2 algebra. You discuss that okay, dx by dt is that. So, dx by x is nothing but a times dt, and then if you take integration both sides, then dx by x is ln x, okay, and it has to be a times t plus some constant, and this constant I am interpreting that is ln of c. Okay. Then this ln and I can take it to left hand side and tell ln x minus ln c. So, that is nothing but ln of x by c is equal to a times c, a times t. By the way, ln is natural logarithm with base c actually. So, once you have this equation known to us, then x by c is nothing but e to the power a t, okay. X by c is e to the power a t, and hence x equal to e to the power t into c. Okay. So, but that is c is an arbitrary constant. So, we have to evaluate that. So, initial condition is known to us. So, we will put that at t equal to t0, x equal to x0. So, that is x0 equal to this equation now. So, c is nothing but the solution of that. So, that is if you take this one to the other side, then c is nothing but that, and hence if you put them together, c is this e to the power negative exponential e to the a times t is 0. So, I put it back here, okay, and try to combine. What I get? I get x of t is nothing but e to the power a times t minus t0 into x0. Okay. And if some cases we assume this t0 initial time is 0, then it is simply e to the power a t into x0 with the assumption that t0 is 0. Okay. In general t0 is not 0, then this is the solution actually. Okay. And what is e to the power a t? E to the power a t, if you expand it like an x power series and all, this is the form actually. E to the power a t is nothing but 1 plus a t plus a square t square by 2 factorial, all that actually. Okay. and as I told, if t 0 happens to be 0, then the solution is e to the power a t into x 0, because that t 0 is 0 simply. Now, this is a very standard thing that we know already, okay, that from Prost algebra actually. Now, what you are going to ask is a little bigger question and tell, okay, what if the equation is something like this, x dot equal to a x, remember this b u term is not there, okay. And all these lectures will talk, I mean this particular lecture especially we are concerned about linear system. So, it is the system dynamics is x dot equal to x plus b u, but the b u term is still not there, and that we are still talking about homogeneous system, linear, and but there are vector equations now actually. So, there are number of equations put together actually. So, x dot equal to x, and then what we want to do, we want to find some solution to that with the knowledge that we have x of t 0 equal to x 0, that initial condition knowledge we also have. Okay. Now, how do we do that actually? So, now let us try to find out some solution by getting inspired from this solution actually, whatever solution we have, we want to get inspired from there, okay, and then tell, okay, can we really talk about a solution in that form actually. So, what we are doing here, we will try to formulate something like this. Remember, the solution here is x equal to e to the power a t into c, okay, where e to the power a t is like this. Okay. So, exactly similar way we want to define and tell, okay, x of t, let us guess a solution that way, x of t is e to the power a t into c, where c is a constant vector, and e to the power a t let us define very parallel to what we know already. Okay, a is a square matrix, remember that. So, a square, a q, all that thing are defined actually. So, whatever we have here, we will just define a very parallel thing to that. Okay. Definition wise, it is very much possible. So, we will just define e to the power a t that way, and then tell, okay, let us guess a solution that way where c is a constant vector. Okay. Now, why are interesting? Why do you have to guess a solution? Now, this is where this uniqueness theorem will come into picture, and it tells only there is only one solution actually. Okay. So, in other words, you can write the solution as sin of omega t, I can write it as cos of well 90 minus omega t, something like that, but then the results are same anyway. Okay. So, that is the greatness of uniqueness theorem. So, what you are interested here is we will guess a solution and try to see whether that is a solution. If that happens to be a solution, then that must be the solution, because there is a uniqueness theorem, the solution cannot be different actually. So, that is the motivation for doing all this actually. We want to guess a solution and let us try to see if it is a solution really. Okay. So, if it is a solution, then this should be the only solution basically, that is the logic actually what you are leading to. Okay. So, anyway, so this is the form that you are defining, and whether how do you know that this is actually a solution or not? So, you can simply verify by substituting, because we already know the form of the solution. So, whether it is a solution or not, simply substitute it there. So, we will substitute to the left hand side, remember c is a constant thing. So, it will come out of that thing differentiation. So, we are having this, but this is actually, remember, e to the power a t is a matrix. So, d by dt of a matrix, that is what we are talking actually here. But by definition, d by dt of a matrix is nothing but element by element differentiation. So, that is some of the things we have discussed while doing matrix theory revision actually. We have done some 3 lectures here for the revision of matrix theory. You can see some of those towards the end of those classes we discussed about how do you define this differentiation integration and some associated results actually. So, this is actually a matrix, and the d by dt of that means element by element differentiation, that is what I mean here, and then a times x is nothing but that, so, a times that actually. So, that is I am just substituting there. Now, let us do further things. The result is like this. Okay, e to the power, so we want to do this actually, right, d by dt of e to the power a t, what is that? I mean that is what we want to see. Now, e to the power a t by definition is that is what we have started with. So, d by dt of e to the power a t is element by element all these actually. So, this means okay, if you have a matrix, you remember that we discussed before, d by dt of okay, a plus b is equal to d by dt of a plus d by dt of b, that is a standard result which will come from simply definition and all that actually. Okay. So, if you have this, if you use that I mean expand these results and use that further, then d by dt of all that is nothing but d by dt of that plus d by dt of that plus d by dt of that, like that actually. and then we are left out with an option here that A matrix is a constant matrix actually. Okay. If A matrix is a constant matrix, we do not have to talk about differentiation inside and all. That is where this time varying linear systems and time what is that linear time invariant systems are different actually. When you have the linear time varying system, this e to the power at solution is no more valid by the way. Okay. What we are talking here is linear time invariant system really. Okay. So, these are constant matrices. So, it can take out from this differentiation process and tell okay differentiation of t with respect to t is 1. So, that is what it is. Differentiation of t square by 2 factorial is that one, and differentiation of t cube by 3 factorial is that one, and things like that actually. Okay. Now, remember this is an infinite series really. Okay. So, I have a luxury of taking an a common, this is 0 anyway. So, I will discard that, and then I will take a common which pre multiplies to everything, and then I will be left out with this series actually. And fortunately, this also happens to be e to the power at. So, what you are having here d by dt of e to the power at is nothing but a times e to the power at, which is very close to what we already know in scalar system. D by dt of e to the power at okay, is nothing but a e to the power at, which is very close to what we already know for scalar thing. That means, if a is a scalar, then that is what it is actually. Okay. So, this is in this definition it also satisfies that way actually. So, d by dt of e to the power at is nothing but a times e to the power at, that is what we want to show here. Now, what you do here, we got something here d by dt of e to the power at. So, we will substitute that. Okay. So, that is nothing but a times e to the power at times c, okay, obviously c comes from here, is equal to that actually. Okay. So, that is what we write here. So, what is it now? If you see these are same, right, the matrix multiplications do commute, right. A B C is equal to whether you take A B times C or A times B C. So, that you see A times B into C or A times B into C. So, that so in that sense their associative law is valid in the multiplication sense for matrix theory. So, that is how it is true, and hence what you have done here, all that you have done is we have verified that this guess solution what we started with is actually a solution, and hence it is the solution actually. Okay. Now, this is not the end of the story, because this is a form where the C is unknown and things like that actually. So, we want to kind of do further analysis and find out the C, and then only you will get a complete idea of the solution actually. So, let us try to do some of this further processing of this. Okay. So, we want to apply the initial condition now, right. Remember, this is a solution, right. So, what is the initial condition is that. So, we want to substitute it. So, x 0 is equal to e to the power a t 0 times c, right. So, that is what we are doing here. Okay. And hence, c is nothing but this inverse actually, e to the power a t 0 inverse of that. Now, there is a great theorem, okay, in the matrix theory, which tells us that e to the power a times t 1 plus t 2 is nothing but e to the power a t 1 into e to the power a t 2, okay, which is not very difficult to show actually. Okay. You can show that using this rather easy. E to the power a t 1 is, we know that formulation, right, a t 1 plus a t 1 square by 2 factorial like that. Okay. And e to the power a t 2 is nothing but I plus a t 2, okay, plus a t 2 square by 2 factorial like that actually. So, if I take e to the power a t 1 plus t 2, okay, that is by definition e to the power a t 1 into e to the power a t 2. So, I have to simply multiply things like that. So, you have you can multiply these two series, this series and that series. Okay. And then simplify these terms and then things like that, and then you can easily show that is true really actually. Okay. E to the power a t 1 into e to the power a t 2 will result in e to the power t 1 plus t 2 terms actually. Okay. So, you have this okay, probably one term I can show you, I plus a t 1, let us say further things are there. Okay. This is I plus a t 2, okay, further things are there. So, this will result in first one I into I. So, that is there. The second one will result in a T1 resulting from here, okay, right, and then it will result in a T2 also, okay. Then it will result in different that what is that a square T1 T2 and things like that actually, okay, it will result in some of these things actually. Okay. Now, if you consider this first two terms, this is nothing but a into T1 plus T2. So, what you have here, okay. This if you just consider up to linear term, this is nothing but e to the power a t basically, e to the power a T1 plus T2 actually, right, is not it, because this e to the power a t by definition is this one. If I expand, this is nothing but I plus a into T1 plus T2 plus further things. So, first order terms I have shown you actually, second order terms and all that you can probably derive yourself actually. Okay. It is essentially just by plugging the definitions and so basically that way. But also remember that this is true in general, okay. This particular thing what you see, that is true in general, okay. However, this also remember is a comment sort of thing, that suppose you have e to the power a t, okay, okay, or let us say a plus b into t, okay, if you have that, right, that is in general not true to e to the power a t into e to the power b t. Even though the left hand side is defined, the right hand side is not equal to, okay, and this is equal to, okay, in general, okay, this is in general not true, but e to the power a plus b into t is equal to e to the power a t into e to the power b t, okay, provided, okay, a and b commute actually, that means a b equal to b a, you can show that, okay. That is the condition that is necessary actually, okay. That if a b equal to b a, then it happens. And the other case what we discussed is something like this, a into T1 plus T2, which is actually like e to the power a T1 into e to the power a T2. Remember T1 and T2 are scalar actually. So, T1 T2 is equal to T2 T1. So, that is invariably true sort of thing, okay. That is true, always true basically, okay. This is first one is not necessarily true, that but it is true only if a b equal to b a, okay. You can show that yourself probably. All right. So, where are we? We just stopped like that. So, this result is there. So, let us try to exploit this result actually, okay. So, what you do? We take a special case where you assume T1 is equal to T0 and T2 is equal to minus T0, we just assume that, and then this result will show that this is e to the power 0 and e to the power 0 is identity, okay. That is identity matrix, nothing but e to the power a T0 into e to the power a minus of T0, okay. Why is that? Because this, why are doing that? Because this in inverse matrix what is popping up here, we really do not know how to evaluate actually, that is what we want to simplify here, okay. So, using this result what you have here, okay, it also very clear that some matrix into some other matrix is identity. Obviously, these two matrices are inverse of each other. So, that tells me that e to the power a T0 inverse what we have here is nothing but e to the power minus a T0, that is all, okay. So, if I substitute this result now in the expression what I already have, then x of t is equal to e to the power a t into e to the power, okay. What was the result by the way? The solution is e to the power a t into c, okay, and c is nothing but this term. So, e to the power a t into this inverse into x 0. So, e to the power a t into this inverse is nothing but that, okay, this e to the power minus a t 0 into x 0, and again I will excite this relationship what you already know, I will again excite that to combine this actually. Now, e to the power a t into e to the power a minus a t 0 is nothing but e to the power a of t minus t 0. So, I am using this result one time to evaluate this one, and then once I have these results back into put together, then I excite this result one more time and combine them together and tell that is what it is actually, that is my solution. So, finally, what we are getting? We are getting x of t is nothing but e to the power a of t minus t 0 into x 0, that is the solution actually, okay. So, that is the solution for homogeneous time invariant linear systems actually, and if T0 happens to be 0, then we know it is e to the power 80 into x0, that is the standard solution anyway. Alright, now let us go to the next one. The next one is non-homogeneous system, now linear differential equations, linear differential equation, time invariant linear system, but it is a non-homogeneous system, that means BU term is there, and that is our ultimate objective. But here also remember that this u of t, we assume that it is known to us as a function of time, that means somebody has given us a control vector as a function of time or as a tabulated value of numbers, something like that. Yes. We are not designing a control per se here, we are just interpreting the numbers that are available to us as simple time varying numbers actually, what are given to us already basically, and these are the initial conditions are known to us. So, we know that this non-homogeneous differential equations will admit solution in two parts, one is the homogeneous solution, the other one is particular solution, and homogeneous solution is the solution without this term that we just derived, and then there is a particular solution. Okay. The catch here is the difference here is the initial condition needs to be satisfied for the total solution, it need not be satisfied with respect to only the homogeneous solution, never actually. Whatever initial conditions are given to us anywhere in the differential equation, they must satisfy with respect to the total solution actually. So, that we should keep it in mind. So, what we are doing here is we are taking the homogeneous solution as it is. Okay. Let us dump this initial condition information here also, and the particular solution we take it this form where C of t will adjust, so that the initial condition also gets satisfied for the total solution. Okay. We are taking the same initial condition here by the way, but this C of t is still there with us, we want to adjust it later, so that the total solution will also satisfy the same initial condition actually. Okay, that is the thing. And this method of variation of coefficient or parameter, what is called, this x of p will assume in this form again and try to derive what is this C of t, that is what the idea there actually. And C is not a constant, but it is a time varying vector, remember that. Okay, it is a coefficient vector, you can say that way. Okay, not a constant vector, it is a coefficient vector. So, now we want to derive what is this x of xp of t, and then we will want to see whether this initial condition is satisfied for the total equation or not actually. So, what are you doing here? So, xp is a particular solution, so it must satisfy the differential equation also. So, we substitute it back in the differential equation and tell okay, x dot equal to x plus bu, let me substitute this term here. So, if I substitute it back, this is x dot is nothing but d by dt of this term, this entire term, and both the terms are time varying, remember that. So, I cannot take one out of this differentiation process really. Okay. So, let us just keep that in mind. So, substitute back here and try to see what you are getting there actually. So, d by dt of this particular term is nothing but d by dt of one term into that plus d by plus this term into d by dt of that is the standard result actually, right. So, this result that we discussed in vector matrix theory, d by dt of let us say a times b is nothing but d by dt of a into b plus a times db by dt, you can say that way. Okay. And the catch here is you cannot alter the sequence of operation, it is very close to the scalar result, but you cannot alter the sequence of operation actually. Okay. Alright, so that is what it is. So, we apply this here, d by dt of this is nothing but d by dt of that into that C t plus this matrix e to the power a t into d by dt of C t. So, that is what we do here. Okay. And then we also note that should be equal to x plus v u. This is x dot, right, this left hand side, this part is x dot, that is also equal to x plus v u, and x is nothing but that actually. The e to the power a t into c is nothing but x actually, right, that is what our particular solution tells that. Okay. So, we substitute that there and then tell okay, very clearly we notice that these two terms will cancel out. Okay. Once the terms are cancelled out, we are left out with C, this term is equal to B u, and hence C dot is equal to e to the power a t inverse, which is e to the power minus a t, that is the inverse term, into B u. Okay. alright. So, if this is the term, what is the good thing about that? Remember, B is a time invariant matrix, that is just a number. U is a function of time that is given to us as a function of time, actually we are assuming that, and then what you are assuming, e to the power a t or minus a t is actually a function of time. So, everything that is appearing in the right hand side vector, ultimately this is a vector, remember that, is a function of time only. So, here is a vector differentiation, the d by dt of c vector is equal to some time varying vector, okay, which are all functions of time only. The c term does not appear in the right hand side. Once you have that, then c of t is nothing but integral of this value. d by dt of some vector is equal to some other vector, right, and which is only a function of time. So, if we tell c of t is nothing but integral value of what happens to the right hand side actually, and that is how we write here. And purposefully we introduce a variable t1, so that we need to adjust the t1 to satisfy the initial condition for the total solution. Okay. So, it is integrated over t from t1 to t, where t1 is a variable now, and let us try to fix that actually. Okay. So, what is xp with t1 intact, okay, e to the power a t into c, but c is also given like that. So, the xp is nothing but e to the power a t into that. Okay. About e to the power a t, remember t is just an integral limit actually. So, it is not a variable of integration. Okay. So, I can push this term inside and then combine these two. E to the power a t I can put it inside, because as far as integration the operation is concerned, this t is actually not tau is different than t, and this t is just a constant number sort of thing. So, I can put it inside and then I can combine these two terms and write that way. Okay. So, xp is nothing but this integral t1 to t with that term actually. Okay. So, now I put them together. So, I tell xt is nothing but xh plus xp, okay, homogeneous solution for plus particular solution. Homogeneous solution is that, plus particular solution is that, where t1 is still a free variable, remember that. Okay. Now, we will put the initial condition which tells us that at t equal to t0, my x is x0. This is my solution for any point of time, but t equal to t0, that is also my solution. So, I will put that solution back, x of t0 is x0. So, that is x0 is equal to x0, because remember t equal to t0 means this is e to the power 0. So, e to the power 0 is identity, right. E to the power 0 is certainly identity, this is e to the power 0, that means all 0 0 0 everywhere 0, this is only left out with identity anyway. Okay. So, that is what I will put it back and tell, okay, that is my identity. So, that is I left out with only x0 term here, and then this integral actually. Okay. So, what I am getting here at t equal to t0, x0 is equal to x0 plus some value, okay, where t has become t0 actually, because I am substituted t equal to t0. Okay. Now, this integral must be 0, because x0 is equal to x0, right. So, this integral must be 0, no matter whatever is my b, whatever is my u, whatever it is, and the way it should happen to be 0 is when I take t1 equal to t0. So, when the this integration happens to be from t0 to t0, then only this integral will be 0 actually, other than the trivial condition that, okay, one of the term is always 0 and things like that, we kind of do not consider those trivial conditions. So, we will tell in general what happens is this integral has to be 0, and that integral happens to be 0 only when t1 is also equal to t0. Okay. So, that is how we get a value for t1. So, once I get the solution, value for t1, everything is known to me, x0 I know, everything is known to me inside each other. So, the solution happens to be this form actually. Okay. Solution is e to the power a into t minus t0 into x0 plus this integral, where the lower limit is t0 to t now, the limits of integration t0 to t with that term actually. Okay. So, also remember the integral term in the forced solution is like a convolution integral actually, it is actually a convolution integral, right, e to the power t minus tau into b tau, things like b times u tau and all that actually. So, that is just a, that means that has some impulse response characteristics and things like that, you can visualize that way actually, but the point to note here is it is like an integral, it is like a convolution integral actually. Okay. Anyway, so we will also see an example to how to make use of these equations and things like that actually. So, we will also make it clear about this solution form. Now, also before we proceed further, also remember that most of the time we also design the u as a feedback form, that means u equal to minus kx. U is not really a function of time. The moment it becomes a function of time, it is an open loop solution really, okay, because you are ignoring everything else, you just apply the control with some predetermined function of time actually. So, that is how the open loop control is defined. So, we do not do that, most of the time we do state feedback form, it is the nicest form ever actually. I mean, sometimes we do output feedback also, but we can, in general we visualize that as state feedback form. And then if it is given to us in a state feedback form like that, okay, then the life is also become easier, because we can say x dot equal to x plus bu, right. So, bu you replace that as minus kx. So, what you get, x dot equal to a minus bk into x. So, that essentially if you define a closed loop matrix as a minus bk, then is essentially very equivalent to a homogeneous system. So, this is the closed loop system dynamics happens to be a homogeneous system. So, homogeneous system solution we already know basically. So, x of t in that case will be something like this, e to the power a minus bk whole into t minus t 0 into x 0, I mean that is how it is actually. So, this form is essentially relevant only when the control is given to us as a function of time, nothing else actually, it is not given to us in a state feedback form actually that way. Alright. So, some of the comments is also before we proceed further. What we derived just now, first of all, nowhere we have mentioned that t has to be greater than equal to t 0, t can be less than equal to t 0 also, right. So, that means the solution is equally valid forward in time as well as backward in time, okay, that is what it is. And as I told you, the integral term in the force system solution is a convolution integral. So, that means the contribution of input u t is the convolution of u t with respect to this e to the power a t times b. Okay. So, what does that mean? This e to the power a t times b has the role of an impulse response of the system, whose output is x t and input is u t. I mean that is just a comment actually, you can see that way. And for output we really do not have to do one more time, because we already know x of t now and u of t is given to us actually. So, y of t is nothing but c of x t plus d c into x t plus d into u t, that we really do not have to do it again actually. So, these are all the small comments that you can probably remember before you go further. Here is the example, let us try to use it whatever knowledge we have for a simple problem. The simple one dimensional motion of car with a force F t. Okay. So, if you simply use this Newton's law, it tells us mx double dot is equal to f of t without any friction, there is no friction, no drag, nothing actually, just tells us mx double dot is equal to f of t. So, x double dot is 1 by m into f of t obviously, and you also assume that mass of the vehicle is constant here. That means what are you telling here? So, if you x double dot is this equation, so first thing to start with is to put there in the state space form, first thing to start with. Okay. So, we define v as x dot, okay, and then tell that is my system dynamics, I write the x dot is nothing but v, this is 0 1 and then this 0, and v dot is nothing but this fellow. So, that means this is 0 0, this is 1 by m here. So, this is your A matrix and this is your B matrix actually. And also we also assume that the initial condition is known to us, x 0 is nothing but x 0 v 0, which is known to us actually. So, we want to find a system solution for this with the assumption that f of t is known to us actually, that is the problem, starting from this initial condition of course. Okay. So, let us see that. So, this is the solution that we already know. Okay. Remember this t 0, we are assuming it is 0 basically. Okay. So, t 0 is 0. Okay. Let me write it properly. Assume t 0 is initial time is 0, initial states are given like that, this is known. Okay. Okay. And mass is assumed to be constant, there is no friction. Okay. This equation tells you that there is no friction, that essentially involves no drag actually, no friction, no drag, mass is constant, t 0 is 0 and initial conditions are known to us, several assumptions actually. Okay. Just a one dimensional problem also. it is not coupled with any other direction. So, it is a simplest problem. It results in two state system dynamics, because the Newton's law is all related to double dots of the position. That's the reason actually. Alright, so now x of t is like this. So, that is what we know actually, we just derived that, where e to the power at is that. Okay. And in this particular case, it so happens that this is our A matrix, and then if I substitute there, then S square onwards it is all 0 actually. So, it is results in I, which is identity, then A times t plus A square will be 0. If you see, if you can do it yourself probably, 0 1 0 0, we multiply that with, okay, you can 0 1 0 0, multiply again that with 0 1 0 0. If you see that, that is actually nothing but 0, because 0 times 0 plus 1 times 0 plus the second one is 0 times I mean this 0, essentially what I mean is 0 0 actually. Okay, multiply this 0 times 1 in 0 is then 1 times 0 is 0, second one, then the third and fourth and all that actually. And in general, this the characteristics actually, just to tie up with matrix theory a little bit, this is something called idempotent matrix actually. Okay. That means, at some power, some finite power of A, it is 0, and hence the further powers of A are also 0. These are called idempotent matrix. And one thing that satisfies this kind of matrix property is all are 0, including diagonal elements being also 0, but off diagonal there can be something actually. Okay. Lower diagonals are all 0. I mean, this is actually a triangular matrix, okay, with diagonal elements also being 0. Okay. If it happens to be like that, then it is a special class of idempotent matrix, somewhere it will happen to be 0 actually. Okay. So, you can also see that this is a 2 by 1, I mean 2 by 2 matrix, where only 1 was there, okay, in the corner, right. So, this matrix what you are talking here, right, you have only 1 here, okay, 0 0 here, 0 here. So, it is a idempotent matrix. So, it turns out to be just this actually. Okay. The beauty of this is this series expansion is exact now. Series expansion is not an approximation anymore. Okay. So, we put it here that I 1 t 0 1 here, and then tell, okay, e to the power e minus tau. What is that? E to the power e minus e to the power e times t minus tau. What do we have to do? We know e to the power a t. Okay. So, wherever t appears here, we just substitute that by t minus tau. Okay. So, t appears here, so we substitute by t minus tau here, that is all actually. So, e to the power a t minus tau is known to us, and then the next thing is to multiply that with b vector actually. Okay. So, this matrix multiplied by that is actually 1 by m into that actually. Okay. So, that is this matrix 2 by 1, I mean sorry 2 by 2 multiplied by 2 by 1 is nothing but a 2 by 1 matrix, that is known to us actually. Okay. So, alright, so we know all these bits and pieces now, because this is the solution that we wanted to do. Okay. And then B matrix was known to us, e to the power a minus t we just found out, e to the power a minus e to the power a times t minus tau into B also we have found out. So, we will now substitute all that and then see what it results in actually. Okay. So, it will so happen, I mean I think it is a very straightforward exercise here onwards. So, it will so happen that it is x of t and v of t will be given that way actually, you just substitute it back, that is all. X 0, remember x 0 is nothing but small x 0 and v 0, these are initial conditions. So, you substitute it there and then try to simplify, it will result in that actually. Okay. So, special case if you take that, okay, let us say that f of t divided by m is a constant. Okay, in general, that means if you have it, okay, let us say it is a car motion probably, it is not a rocket motion, then m is a constant quantity fairly, and then f of t by m is also constant quantity, provided f is a constant quantity that way. So, if that happens to be constant and initial position and velocities are also 0 0, okay, then I can really simplify this to that way actually. Okay, this entire expression what I have here, okay, remember x 0 and v 0 are 0 0. So, all that thing will be 0 0 0 here. Okay. This is a t square minus a t square by 2. So, it will result in half a t square, and v t is nothing but a t. So, this is also very compatible with what we know in +2 physics actually. That means, u equal to a t and s equal to half a t square, probably that is the thing that we have studied before. and so that is actually compatible with several assumptions like that. Okay. That means all in addition to these assumptions what you are telling, no friction or no drag, then T0 is 0, initial conditions are known to us, and on top of that if the acceleration is a constant quantity, okay, and position and velocity initial conditions are both 0 0, not just a number but is 0 0, then these results are like that actually under several assumptions actually. So, what is the utility of the state space system dynamics? First of all, this is a verification, and the utility is a lot more than this. It tells, okay, any system dynamics that is of any dimension, need not be only 2 dimension, things like that, you need not have several assumptions like that, we can still get a solution actually, right. So, these solutions what we really know from our earlier knowledge is no more valid, whereas this solution what we are talking here is very much valid. We can have a time varying force, we can have let us say T0 not equal to 0, things like that, you can still get a solution using this formula actually. Okay. And then f of t can be arbitrary also, need not be a constant quantity. F of t in general can be some function of time, let us say sinusoidal function of time, whatever it is, you can still get a solution and know the position and velocity of the vehicle actually. That is the beauty actually. Now, before we conclude this lecture, we will see e to the power at evaluation. Okay. Remember this linear systems theory, we can never escape this reality that e to the power at comes back to us repeatedly. Okay. We as long as we talk about linear time invariant system, e to the power at is a universal reality actually. Okay. So, people have paid lot of attention to get the quick way of evaluating e to the power at, or a good way with less approximation errors of evaluating e to the power at like that actually. Okay, a lot of attentions have been focused like that. So, let us see one attention, one result that is very useful later actually. So, what is that? I mean, if you have the solution, if you have a system equation like this, x dot equal to x, where x of 0 is actually x 0, then the solution using Laplace transform is like this. Okay, you use Laplace transform here left hand side, s into x of s minus x 0 obviously, and that is the Laplace transform result is nothing but a times x of s actually. Okay. So, then you talk about okay, what way I can simplify this. So, I take x 0 to the right hand side and this one to the left hand side and tell s I minus a now into x of s is x 0. So, x of s is nothing but s I minus a inverse times x 0. So, this is my Laplace transform result. Okay. And then from here if I take inverse Laplace transform, then x of t is like that actually. Okay. However, this problem, this homogeneous time invariant system admits this solution, we know that, right, that is we just derived actually. So, if you equate these two, it is very obvious that e to the power at is nothing but this expression, Laplace inverse of s I minus a inverse. So, you first you have to do s I minus a, then you talk about s I minus a inverse, that is a symbolic representation of inverse matrix, and then you talk element by element Laplace inverse actually, then you will get e to the power at basically. So, how do we get that? Now, in a 2 by 2 problem it may be simple, 3 by 3 probably you can do, but as the dimension of the matrix increases you cannot do actually. So, then people have thought about how do we do that in a good closed form solution way actually, how do you come up with in a very efficient manner, how do you, I mean, is there any numerical algorithm that can be devised actually. So, let us see that quickly. See, A is something like this, it is a n by n matrix. So, these are elements all over. So, S I minus A is obviously that, this is just an algebra, A matrix is that, so S I minus A is that, and S I minus A inverse is nothing but adjoint of this matrix divided by determinant of that matrix. That is from very straightforward result actually. Okay. Now, we need to find out the adjoint of this matrix and the determinant of that in a very efficient manner, that is the problem actually. Okay, that is all we are talking. We are talking about evaluating this S I minus A inverse in a efficient manner. Can we do that? Now, S I minus A, remember S I minus A determinant is just a scalar quantity, right? Determinant is always a scalar quantity, and S I minus A is that one. Okay. So, n by n matrix, remember one term is multiplication of these diagonal elements, right? First term is multiplication all that. So, that will result in nth order polynomial. Okay. So, S I minus A in determinant is nothing but an nth order polynomial. Let us write that nth order polynomial as like this. So, s to the power n plus some coefficient s to the power n minus 1 like that actually. Still remember this is scalar value ultimately. Okay. Now, adjoint of Si minus A is a matrix, okay, but adjoint means I have to, so let us say I talk about adjoint of I mean this matrix, adjoint matrix is nothing but cofactors of the elements arranged in different places obviously. So, if I take the cofactor of this element, that means I forget this and forget that and then talk about that one, right, somewhere. So, that means this fellow is nothing but a n minus 1/3 order polynomial, because one term is gone already. Okay. However, this is actually a matrix. So, the coefficients will be matrix, but the polynomial of each of the I mean elements of that matrix will contain at the maximum n minus 1/3 order polynomial. Okay. So, you have n minus 1/3 order polynomial out here, e to the power n minus 1 here. So, E1 is nothing but a matrix here, E2 is a matrix, but the polynomial coefficients are n minus 1, n minus 2 like that actually. Last element is just En actually. Now, we have to find out a logic for which we can quickly compute this A1, A2 up to An and E1, E2 up to En actually. That is our problem. If you do that, we are done actually, because we know that actually anyway. Now, how do we do that? Let us do that. Okay, let us multiply this equation. This one is equal to that. So, we will multiply that and that is equal to that. That is what we are doing here. Okay. Just simply multiply that actually. Okay. So, let's we substitute here, that means this adjoint of this we substitute back here, determinant we substitute back here, and then this Si minus A will multiply both sides actually. That is all we are doing actually here. Okay. Si minus A into Si minus A in inverse is nothing but Si minus A into adjoint of this is nothing but that, by determinant of that is nothing but that. That is all we are doing here. Now, this is nothing but identity, right, this matrix is identity obviously. So, I times this one, all that is nothing but this one numerator, whatever numerator you have, this is identity times this polynomial is equal to what we have in the numerator. Okay. So, now what I have, I can expand this this polynomial in the left hand side, and hence I will get s to the power n into I plus A1 times s to the power n minus 1 into I, things like that in the left hand side, and the right hand side is all given like this actually. You can simplify that. First term is s to the power n, second term will be s to the power n minus 1. I just take common and I will left out with that actually. Okay. So, what is the beauty of that? I have a polynomial of n third order. Okay. These are all matrices now with I, remember that I is multiplying everywhere. So, that is all matrices. Okay. So, I have a polynomial matrix in the left hand side, I have a polynomial matrix in the right hand side. So, I can equate the coefficients actually. So, if I equate the coefficients, what am I getting? E1 is nothing but identity. Okay. And this term E2 minus E1 is nothing but A1I and things like that. So, E1 is I, E2 minus E1 is A1I and things like that actually. Okay. So, what is there? Suppose E1 is identity. So, E1 is very clear, E1 is I simply start with I. Now, if I know this A1, A2 up to An, okay, all these, then E2 also I know, E2 is nothing but A1 plus A1I, E3 is nothing but A2 plus A2I, things like that. So, the question is, can I know this A1, A2 values actually, A1, A2, A3 up to N values, and fortunately it so happens that AI can be computed that way. This part I will not show actually, this is there in this book preview, you can see that actually. Okay. So, AI can be computed that way, that this suggests a recursive algorithm really. What means E1 I will start with I, then I will quickly compute A1, A1 is given like that 1 by 1 into trace of A times E1. So, that is A1 I will be knowing actually. Once I know A1 I can compute E2, once I compute E2 I can compute A2, once I compute A2 I can compute E3 like that actually. So, this is a recursive algorithm which you can make use of actually. Ultimately remember that I am done here, that means En is equal to that, I am done with that. So, the last equation what I have is simply for verification purpose, that is all. E1 to En, that is all we require, right. If you see that, all that we require is E1 to En and we are done here, last but one equation. So, the last equation is there only for verification purpose actually. All right. Ultimate, this is just a method of evaluation of e to the power at. Now, let us discuss a little bit about time varying system, because that is what we have not discussed before. And in general we know that solution of I mean the linear systems can be time varying as well actually. So, let us quickly discuss about this homogeneous linear systems, that means Bu part is not there, but A of t is now a function of time. Now, if that happens, the solution happens to be in this form, where this phi of t tau is nothing but a what we call a state transition matrix actually. So, it takes one state at a particular point of time and then transits to a different point of time. It takes a state at let us say time tau and it gives a value of state at time t. So, that is the state transition matrix. It transits this state to this state actually. Okay. Now, there are very nice properties that are available for state transition matrix. Remember, the state transition matrix has no closed form solution in general. Only if it is time varying, I mean time varying thing goes to time invariant thing, that means A of t is really a constant matrix, then this phi of t tau is nothing but like a exponential t minus tau and things like that. So, that is only special case, otherwise in general these state transition matrices do not have closed form solution. However, they satisfy these nice properties from which you can actually derive a neat numerical solution very quickly. Because the first equation is nothing but this one, which is very similar to what the state equation is. X dot is dx by dt is a of t times x. So, del phi by del t is nothing but a t times phi. But this differential equation is a vector differential equation and this differential equation is a matrix differential equation. Phi is a matrix, remember that. So, to obtain a vector solution, we have to actually get a metric solution first and that needs to be done in a numerical way in general. Okay. But for the numerical solution also you need an initial condition, I mean either numerical or closed form whatever it is, you still need the initial condition. An initial condition fortunately is given like that, because if you freeze any t, not necessarily t0 any t, then x of t is equal to x of t, that means this matrix is nothing but identity. So, it is also valid for t0 basically. So, if you have any time substitute phi of t0 is identity anyway. Okay. So, this equation coupled with this equation gives us a complete information. So, this is a matrix differential equation and this is initial condition. With that we can integrate this equation numerically, because a of t is not a constant number, that is the problem actually. Okay. And if you can integrate it in a closed form, well and good, because the a of t, if it is time varying, in practical system they are not given as nice functions of time, they are not like linear function, quadratic function, sinusoidal function, not like that. They will be typically given to us in the form of numbers actually, that is the problem. Okay. Otherwise you can think of numerical closed form integration also actually that way. Anyway, for now there is another property which tells us that for any 3 different points of time t1, t2, t3, t3 t1, phi of t3 t1 is also like phi of t3 t2 and t2 t1. So, this is interesting. Suppose you have this t axis, then you have t1 here, t2 here and t3 here. Suppose you want to know this this x of t3 probably, and then correspondingly you can jump from here to here and then there to there. Okay. This is similar to what going there actually directly. Okay. So, this will talk about again these results can be easily derived by simply plugging the definition actually. Okay. Now, I suggest that you do some of these derivations yourself. The second one I have explained. Okay. The first and last I suggest that you do yourself actually. Okay. That means it is very easy. I mean if I talk about x3 for example, and I try to transit from x1 to x3, then the resulting matrix is that. So, x3 is this matrix into x1 and x2 is this matrix into x1 if I get that, and x3 is like that actually. So, just substitute the definition and then try to simplify, you will get it very quickly actually. So, these results are very standard for state transition matrix. Now, this is also another thing, that if you want to take inverse of this matrix, then you just have to alter the coefficients actually. I mean this tau t is nothing but t tau inverse. Okay. And for time invariant system, these are very neat. You do not have to really talk about two different variables altogether. If these two variables can be clubbed together in the sense, if phi t and phi tau are there is nothing but phi of t plus tau, and then phi inverse is also phi of minus t actually. Okay. So, for linear time invariant system, as I told before, phi of t tau is nothing but e to the power a t minus tau, which is very compatible to what results we have already got for LTI systems. Now, how do you make use of them in for the time varying systems? I mean, that is what you have to, that is what you have studied that. I mean, the whole motivation is to make use of that for time varying system. So, you start with this guess solution again, okay, and then tell, okay, you make use of the method of variation of parameters, where C vector contains unknown things and all that, exactly similar to what you have done before. We proceed, only remember that e to the power at we cannot talk, we have to simply work with this phi matrix. E to the power at is a special matrix for phi, but in general it is phi is phi. So, x dot, so what is that actually x of t is that. So, x dot is nothing but that del phi by del t into c plus phi times c dot, that is what we have done before in the sense of e to the power at. Now, we will stop this particular thing, I mean will cannot be simplified further, you have to stop here and tell it is nothing but del phi by del t into c plus phi times c dot actually. So, right hand side is also like that, a times x, so the x is phi c plus b u. Okay. So, this equation suggests that c dot is nothing but that actually, okay, because this equation, this one and that one will cancel out. Okay. So, c dot is that. So, c of t is that, okay, exactly similar to what you have done, here it is phi inverse now. Okay. So, x of t 0 is that, phi of t 0 is identity, that is, so that is the thing that we need to remember. So, if you substitute it back, then it turns out that x of t is all that, okay, and this one first term is that and second term is that. I can take this integral inside and then try to club them together, because inverse is altering the coefficients. Phi inverse of tau t 0 is phi of t 0 tau, that is one of the results, and then this one goes inside, and now this is like 3 variables here, t to t 0 and then t 0 to tau, that means I can interpret that as phi of t tau, okay, intermediate variable will go. So, that is what the solution ultimately. So, x of t is nothing but this one. All that is valid provided you have a closed form solution for phi t t 0. This equation is very useful provided you get a closed form solution for phi t t 0. If it is not useful, then probably you can do numerical solution, and if you really want to do numerical solution, then why is doing all the things? I mean, you can just even start with this one and take numerical solution directly basically. So, there is no point in going through the numerical solution of phi and then substituting it back and then carrying out further integrals and all that to get a solution and all. So, my point is you can directly get the numerical solution that way. Okay. Anyway, so that is all we need to talk here. We discussed various ways of this time solutions for linear systems, both for time invariant system as well as time varying system. On the way, we also saw e to the power at, some algebra with that, and as well as how to get a computational way of getting this e to the power at. And here you also remember, all that we have done here is to get these coefficients in a recursive algorithm sense. Once you get the coefficient, you still have to do this Laplace inverse of this matrix, which needs to be done element by element yourself. Just keep that in mind, and various other ways are also there. Probably we can see some of that as we go along actually. All right, we will stop there in this class. Thanks a lot for the attention.